Welcome to our presentation on overcoming challenges and leveraging GANs for few-shot data augmentation. My name is Christopher Beckham, and this work was done in part with Isam Laraji, Pal Rodriguez, David Vasquez, Derek Naruzi-Zarai, and Christopher Powell. To start off, we can give a brief overview of few-shot learning. In few-shot learning, we're concerned with designing algorithms that can easily adapt to new classes that we haven't seen before. And we assume that these new classes might be underrepresented. Maybe there's not enough data, or maybe there's not enough labels. And we know that deep neural networks generally require lots of data or lots of labels in order to get good performance. So it's a big kind of fundamental research topic to see how we can get these deep neural networks to be more data efficient. And existing approaches can be seen as actually incorporating some sort of prior knowledge into one of the three things. The first is the model and architecture. And so maybe these are specific layers or specific architectures that try to facilitate better learning on low amounts of data. The second is the learning algorithm, so things like meta-learning, learning how to learn, and things like that. But we can also look at it in terms of the data. And so a really simple example here would be like data augmentation. Is there some way that we can do smart data augmentation to augment our set of few examples that correspond to those new classes? And in this work, we're actually going to focus on this aspect since it seems to be at least somewhat the least explored out of these three. So specifically, we want to explore data augmentation via few-shot generative modeling. And specifically, we're going to do this with generative adversarial networks, also known as GANs. And we're also going to assume that if you're watching this, that you're sort of vaguely or roughly familiar with GANs and how they're trained. And this is just because GANs are quite complicated on their own and technical, and there is a lot to cover. So we won't go into technical detail of GANs too much. And basically, we assume a setup where we have a GAN that's basically pre-trained to generate from training or source classes, right? So we want to learn a conditional model P of X given Y. And we assume that these source classes are abundant, so that there are many examples per class that we can train a GAN that can do generally quite well in generating from these classes. After that, we want to fine-tune the GAN on basically these target classes. And these target classes comprise very few examples, hence the few-shot saying. And when that's done, we want to use the GAN to actually generate new examples conditioned on these target classes. So we actually want to use the GAN as a data augmentation algorithm to basically augment this set. And we want to use those examples actually to improve the performance of a classifier that's trained to predict from these target classes. And we assume that if we were to train a classifier on just the examples from these target classes, it wouldn't do so well just because we have very few examples. And so we want to leverage a very smart form of data augmentation in the form of a generative model to try and improve this classifier here. So here we have our few-shot data augmentation pipeline, and this is sort of basically the entire pipeline that comprises this work. And it consists of many steps, but these steps are necessary in order to do a principled and rigorous evaluation. So to start off, we have these source classes, and like I said earlier, it's basically assumed that these are abundantly represented. So we have 5 classes here, and we have, if you can pretend, for the sake of this illustration, that we have lots of examples per class. And on the other hand, we have what's called target classes. And here we have, let's say, 4 classes, but we only have 5 examples per class. And so basically, we use this term K to denote K-shot, and K here would be 5. So we only have 5 examples per class. Now, for the sake of evaluation, this is actually a subset of a larger validation set because we'll need this for evaluation later on. But essentially, when it comes to training, we really only have access to these two things. So to start off, we basically train a GAN on these source classes, and then we basically have a fine-tuning step where we try to fine-tune this pre-trained GAN on very few examples from what we call the support set. And from this, we can use the GAN to generate data, so it can act as that data augmentation algorithm. And then from this virtual data, let's say, and from the real examples in the support set, we actually want to fine-tune a classifier. Now, it's not illustrated in the figure, but there is a classifier that was originally pre-trained on these source classes, but now we actually want to fine-tune it. So let me just write this here. We actually want to fine-tune it so that it can perform well at classifying target classes. And eventually what we'll see is that we'll use the validation set to actually validate whether this virtual data actually helps with the classification performance of this classifier. So to lay out our contributions, the first is that we perform a rigorous exploration into few-shot data augmentation with GANs. Unlike some previous works, we have this additional step where we're basically doing a fine-tuning step that adapts the pre-trained GAN to generate from our target classes, rather than sort of do so in what we call zero-shot fashion. So I'll elaborate on this very shortly because sometimes it can be easy to be caught up in the semantics and get confused by some of these meanings. Secondly, our empirical evaluation is actually done over many randomized splits of the data, but these splits are actually done with respect to classes. So what I mean by that is, if you were to imagine, let's say, this being the entire data set, and maybe this vertical axis denoting the number of examples per class, and this horizontal axis denoting the classes, what we can do is that we can sort of do different versions of the data set where essentially we randomize this order and then just cut the data set so that we have source classes and target classes that have been randomized. And so a lot of our results are actually averages over these different what we call data set seeds. And this is to kind of avoid confusion with other types of seeds. Like generally people use seeds to basically randomize weight initialization in neural networks. But here we have dataset seeds to basically refer to the randomization of creating, the randomization involved in creating different versions of the dataset where we have different source and target classes. Next, we shed light on the difficulties involved in doing such a pipeline, as well as limitations with the empirical evaluation of existing work. And to alleviate some of these difficulties, we basically also propose a simple fine-tuning approach that leverages semi-supervised learning. So just to give a bit of background, we can talk about how one might generate new data in what I call a zero-shot fashion. So let's just assume that we have our training set, which comprises our source classes. And we're going to train a conditional model again, that's basically P of X given Y. And we train this GAN, and when it's finished, we can just easily generate something that looks like it comes from this set by injecting some noise, which would commonly be some Gaussian noise, as well as a label. And so in this case, we have 5 labels, so maybe Y is a one hot vector that can basically be one of these 5. Maybe for 9, it would have a label like such, where the 1 here denotes this 9. So that's all easy and straightforward. But if we wanted to adapt the GAN to generate from unseen classes, from target classes, it's not so straightforward. It's not like we can put in a one hot vector corresponding to a label that we've never seen before. That just won't be possible. So one easy way to work around this and it would depend on a lot of details, but I'm going to keep it sort of abstract for now, is that if you had an encoder network that was trained to sort of learn some representation that corresponds to the label, this could maybe be a way to work around it. So maybe if you feed, if you train this encoder with these digits, it kind of learns some like semantic space where digits at a similar sort of close together. And so if you have something like this and you assume that it generalizes, that it will generalize to your target classes, well, then you can basically feed a new target class, an image corresponding to a target class into this. So maybe we feed in an H, which is a class that it's never seen before, and maybe it maps it somewhere in the space. And if we've trained the GAN to actually take in R as the conditioning label instead of Y, then maybe we can get some semblance of generalization, and maybe it will generate something like an H or something close to it. And so I'm calling this zero shot because the GAN hasn't been explicitly trained, or neither the encoder, neither of them have been explicitly trained on these unseen or target classes. We're just hoping that at inference time, it will just work right off the bat if we do this. So in the previous slide, we basically illustrated, just drawing it in blue, this particular portion, where we're basically saying if we had some sort of representation network and everything worked the way that we wanted it to, we could basically feed these digits in as X, extract some semantic representation, and then basically use this pre-trained GAN that was pre-trained on the source classes to actually generate a data set which hopefully looks like this. And again, this is basically what I call zero-shot generation, because we're not using any labels whatsoever here. We're just using the images and hoping that we extract a good representation so that we can generate things that look like they come from this. But things might semantically get a bit confusing now, because you also have this fine-tuning step where you're fine-tuning a classifier using basically you're combining your GAN-generated images with your real images in the target classes, your support set. Where here k equals 5 because we basically have 5 examples per class. And so in this stage, we're actually using labels technically, which is why I'm calling this basically few shot fine tuning. And so this is where things can get a bit confusing, but in this presentation, basically zero shot generation just refers to the fact that we have this GAN and we're not using any of the labels in the support set. We're just going to generate by inferring the labels using this encoder. But on the other hand, one can think of this stage as few shot because we're actually using these labels to fine-tune a classifier. So to put that into context with what we're doing, it's worth saying that in the sort of preliminary work that we did predating this research, we found that this zero-shot kind of generation is risky and unreliable. It's not guaranteed that basically we can have this GAN generalized to target classes that we've been seeing before. Maybe in rare cases it will, but most of the time, in our experience, it didn't. And we also know that deep neural networks do inherit significant biases from their training data, and obviously this can have a detrimental effect on generalization to new classes. And two existing approaches that we'll talk about in this paper basically leverage zero-shot generation. So the first is DARGAN, which actually makes use of this representation encoder network that we talked about previously. There's also matching GAN and F2GAN, which are sort of like conditional autoencoder / GAN hybrids. So they basically combine adversarial learning and autoencoders, but basically both try to do this zero-shot generation. Whereas, like mentioned, with some of the preliminary work that we did, it didn't seem like this was a good idea, and it didn't seem to work well. And so basically one of the big contributions is, even though it's an extra step, we think the right way is to basically fine-tune this GAN in a very smart way, so that we can basically have it be a more reliable network when it comes to generating to these target classes that we've never seen before. On the topic of fine-tuning GANs, there's been some interesting work that's come out in the recent years that is worth talking about. The first is this variant of StyleGAN v2, which actually proposes this thing called adaptive discriminator augmentation. So typically, if you're trying to train a GAN on small amounts of data, then obviously you're going to have to use some form of data augmentation, whether that be random crops or rotations or color jittering, and you're probably going to have to do this very aggressively. But the issue is that these augmentations are actually going to leak back into your generative distribution, and so now when you use that GAN to generate, it's basically going to also apply those augmentations, and that's kind of not what you want if you truly want to actually model the actual data distribution. And so this paper actually proposes a way around that, where you can actually use data augmentation when you train the GAN, but not have those augmentations leak back into the distribution. There's this interesting work, few-shot GAN by Robert Tal, where basically they propose a fine-tuning strategy for GAN, basically by manipulating singular values or fine-tuning them in the generator. And this is interesting because there's sort of like two ways that one can fine-tune a GAN. One could just only consider the generator and forget the discriminator and kind of do something with the generator. Or one can try to fine-tune it where basically you're optimizing the same losses, the same two-player minimax game between the generator and the discriminator, but just doing it very carefully because you're fine-tuning. And so this basically falls into the latter. Interpolation-based autoencoders, maybe this is more under the zero-shot generation realm, but this is just to say that one can actually use autoencoders for data augmentation too, by basically interpolating in the latent space, using some interpolation or mix-up based algorithm. And so generally speaking, a lot of these papers, they have these interesting contributions and algorithms, but they mostly measure their proposed methods with things like perceptual image metrics that basically measure let's say how realistic an image looks. But there is a lot less evaluation on actually measuring the utility of the images that actually come out of these fine-tuned GANs. Like, for example, maybe with these generated images, we want to measure how well it performs on a downstream task, whether that be classification, segmentation, VQA, or something like that. That appears to be less common. So for the remainder of this presentation, we're basically going to go through each of these stages here, just to explain this entire few-shot data augmentation pipeline. And the first we'll start off with is the actual GAN training itself on these source classes. So here we're going to show basically the architecture that we're using for our GAN. So if we just focus on this part for now, we can actually just not consider the discriminator for now. And we can just consider the generator. And generator architecture is actually very StyleGAN inspired, at least architecturally. The idea is that rather than actually directly feeding Z and Y as inputs to the network, we actually have Z and Y basically input to the network somewhat indirectly through this adaptive instance normalization or adaptive batch normalization. And instead, the direct input is actually this learnable tensor. It's basically a constant, but it actually comprises the parameters of this network. And if we were to kind of expand this out, we'd get something like this, where we can see that the Z and Y kind of operates through this pipeline, where Y basically gets fed through this embedding network, and then Z gets concatenated with this and goes through some linear or even a tiny multi-layer perceptron to produce basically scaling and shifting coefficients that basically modulate the feature maps here. And so, I mean, apart from the fact that the StyleGAN authors showed that this architecture is superior to what was previously used, it's also convenient for us because these comprise very few parameters compared to everything else in the network. It's actually convenient to fine-tune, because we can imagine a scenario where maybe we only have to fine-tune these. And so that's one big motivation for this architecture. Lastly, for the discriminator, we basically use a projection discriminator from Miyato et al., which is pretty common nowadays for GANs, and we'll talk about the significance of using such a formulation later. But essentially, nothing special is happening when we train this. We're actually just training using the Jensen-Shannon or logistic loss, and so these are the typical losses that you would minimize here. And so basically, we'll be training this over the training set, which comprises our source classes. Back to the few-shot data augmentation pipeline. With this out of the way, now we can consider the more exciting step, which is actually how to fine-tune the scan. So this here will basically be trying to use the support set to basically fine-tune the GAN that was pre-trained on the source classes. For GAN fine-tuning, we can actually consider 3 different ways to fine-tune either the generator or the discriminator. And so for G, we basically have this acronym called GFM, which is short for G fine-tuning mode. So if we just look at the res block for G, here, I'll just write this down, res block. Basically, we can think of 3 different ways that we could fine-tune this res block, and we're going to do this for all of the res blocks in the generator. But the first strategy is that maybe we could freeze everything except the embedding layers. So we know that the embedding layer is really just a lookup table where basically you're mapping indices corresponding to labels in the source classes to basically continuous vectors. And to fine-tune, one could just easily add rows to this matrix that basically correspond to the labels of the target classes. The second strategy is actually to unfreeze everything except the linear layers, so that would actually be both this layer and this layer. The other strategy could just be to be a bit risky and just say, well, okay, what happens if we just unfreeze everything and just resume training? And so a similar thing can be devised for D. I haven't gone into the architecture for D yet, but suffice to say that one can sort of do a similar thing here. There is an embedding layer for the discriminator, and there are some linear layers at the end of the network in D. So we'll look at this later. But again, we'll call this DFM to be short for D fine-tuning modes. And basically, because we have 3 different ways to do GFM and 3 different ways to do DFM, we get a total of not 6 but 9 combinations in terms of the hyperparameters that we'll have to explore. So once we have chosen a particular strategy, DFM, GFM, then basically we want to resume GAN training on the support set. By resume, we just mean basically still optimizing the same losses that we did when we were pre-training the GAN. So it's the same adversarial game between G and D, but now it's going to be done on the support set. And for early stopping and model selection, basically what we're going to use is basically the Frechet inception distance, which is basically what we also use during training. But here we actually want to compute the FID between the validation set and the generative distribution induced from those labels in the validation set. So if we can imagine this being our validation set, basically we want to take all the labels in here and then basically generate a corresponding fake image with the conditional P of x given y, and then we're going to have our generative distribution here, and basically we're going to compare the two with FID. So now what we can do is that we can do this fine-tuning step and actually visualize the FID on the valid set as a function of the number of epochs that we do on the support set. So what we're seeing is basically some learning curves for emnist k equals 5. And we have 2 curves here. One is when GFM is embed, and the other is when GFM equals linear. And so you can see that there's basically uncertainty computed over both of them, and this is actually the uncertainty computed over the other DFMs. So for example, here this is the uncertainty computed when GFM equals linear, but DFM takes on all the other three configurations. And certainly what's interesting to see is that actually if we only fine-tune the embedding layer for G, we actually get the lowest FID at around this point, which is really interesting. If we monitor the same experiment, but monitor the FID on the training set instead, we'll see this interesting observation, which should hopefully match with our intuition that because we're using GFM equals embed, that the training set FID does not get worse over time, because we're actually not changing any weights in the generator. Well, the embedding layer, the embedding matrix is being changed in a sense, but really we're only adding rows to it. And so we wouldn't expect generalization on the training set to change. But as you can see, when GFM equals linear, you kind of get this catastrophic forgetting effect where over time it's actually performing worse. And so that's an interesting observation, is that when GFM equals embed, you can sort of do this this class incremental learning, where basically we can just add more classes to the generator and not have it forget how to generate from the other classes. And so that's a pretty interesting result as well. Now, this is certainly not to say that under all possible situations that this would be the way that one should do fine-tuning, even though it is neat and we can kind of do this incremental fine-tuning thing. But the question that we might want to ask is, well, when would this work well? And really it depends on a lot of things, namely, how far apart the source and target classes are, and also the features that are learned by G and how expressive they are. And so it's worth remembering, for EMNIST, maybe there isn't such a huge gap between the source and target classes, but we can imagine a situation where maybe this scheme wouldn't work. If we were generating natural images, for example, if the source classes only comprised, let's say, vehicles, and the target classes only comprised animals, well then maybe we wouldn't expect this to work. Maybe we'd need a more liberal kind of fine-tuning setup. But at least for EMNIST, this seems to work the best, which is an interesting result. To give a summary of our findings, specifically for EMNIST, if we try out K equals 5, 10, and 15, the best fine-tuning strategy for the discriminator, so the best DFM, varies quite a bit amongst the different dataset seeds. But really, it's either, all parameters or just the linear layers. We didn't really have much luck, only fine-tuning the embedding layer for the discriminator. For the generator, basically we generally found that embedding or linear basically performs the best, especially embedding for when K is small, like when K equals 5. And yes, for K equals 5, GFM equals embed actually gave the best validation set FID over all the dataset seeds. But when you increase K, you might have to be a bit more liberal and go for linear. For Omniglot, K equals 5, we found that basically linear for G and all layers for D works the best. And for CFAR 100 for K equals 50, we found mostly having embedding for G and linear for D worked best. But for the best hyperparameters over all of the dataset seeds for these datasets, you can actually consult the appendix of our paper, and you'll get those that information there. If we plot the distribution of validation set FIDs for each K, then we can see that perhaps obviously as K increases, we get a decrease in the validation set FID. Here in blue is basically the baseline FID, which is the FID on the training set. Here we get to see some generated samples from the fine-tuned GAN for K equals 5 for the best hyperparameters for DFM and GFM. So here we have basically the 10 classes, the 10 target classes, and then on this axis we have random images generated from that class. Here we also have the same sorts of generated images, but for k equals 10 and also for k equals 15. And these images can also be found in the appendix of the main paper. With both these steps out of the way, now we can look at both the data generating process from the fine-tuned GAN as well as the fine-tuning of the classifier. So we'll explore both of these in the following sections. So what we originally have is a classifier that was originally trained on our training set, which comprises our source classes. And so basically this is a ResNet 18. And so to go through with fine-tuning this classifier, what we're actually going to do is basically completely freeze everything, but replace its old probability distribution over the source classes with a new probability distribution over the target classes. So we're only interested in reframing this classifier to predict the new classes. And this is really just to kind of keep things simple. But one could also, in principle, consider what's called generalized few-shot learning, where basically one tries to also predict all of the classes and sort of like maximize accuracy over all of these. But anyways, once we have this classifier, then we have to fine-tune it with some data. And so we have our support set, where in this particular illustration, k equals 5. But also we have data generated from the GAN condition on these target classes. And the question is, well, how much data should we generate? And so here we have a specific hyperparameter called NS, which is basically the number of augmented samples to generate per class. And so in this illustration here, what we have is that we actually have 10 examples per class, and so we have NS equals 10. And so basically in total we have 40 augmented examples from the GAN, as well as 20 here from the support set. And basically, we would like to combine both of these sets together and use this to fine-tune the classifier, where we want to measure the accuracy of this on that held-out validation set, which also comprises these target classes. So for the classifier fine-tuning, we consider a few experiments. The simplest thing to do, which is this baseline, is to actually only fine-tune on this support set and see what result you get. The second is when you combine it with traditional data augmentation, in particular random crops and rotations. And so here one hyperparameter is this thing basically called min scale, where basically for random crops you basically control what the minimum crop area is going to be. And so this is a hyperparameter which basically essentially dictates how aggressive these random crops are. Input mix-up is an easy to implement and strong baseline. I won't go into that just for the sake of time, but for those details, you can look at the paper. And then basically our fine-tuned GAN, which requires tuning this NS parameter. How many examples per class do we want to add to combine with the set? And so, like I said earlier, the metric that we want to basically used for hyperparameter tuning or early stopping is actually classification accuracy on the held-out validation set, which basically comprises the target classes. Here we present results of our experiments basically on the validation set, and we've also superimposed this with the table from F2 GAN. So this is directly basically copied from Network. And where they evaluate their method and compare it to various other methods in the literature. And so I'm putting the separating bar here just to say that, due to differences in the empirical evaluation, these aren't directly comparable, but it still gives us a bit of information as to where these methods lie empirically. And the first thing to note is that for the F2 GAN experiments, we actually don't have measurements of uncertainty, which is unclear. And they're also using a single source class and target class split, so it's one dataset seed. Whereas compared to our work, basically we actually do get quite inflated variances, which can certainly call into question, some of the statistical significances or practical significances of our methods. As k increases, these uncertainties do go down, however. And another thing to note is that it's not clear if a held out test set was used in F2 GAN's case. And there are a lot of hyperparameters that have to be tuned for both the GAN fine-tuning stage and the classify fine-tuning stage, and so these could potentially be biased estimates. Obviously, in this table, it would be the same thing for us, but in the next slide, we'll show our results on a test set which was not used at all for validation. This semi-supervised result is also interesting. We'll get into this shortly, but this definitely constitutes a really positive result because we actually, amongst our experiments, we get the best result for all the values of k, even if the variances are inflated here as well. So here we present results on our test set. These are the results from the previous slide on the validation set, and basically here, this is when we take the best model that we, which would correspond to the model reported in this table, and then applying that to classify the test set. If we just consider just the non-semi-supervised approaches, we can basically see that for k equals 5, our fine-tuned GAN performs the best. For k equals 10, we also get a gain, even if it's a bit marginal. And for k equals 15, we actually don't do that much better. We actually do worse than these two methods. And so, we'll kind of talk in the following slides about why this might be the case, that why despite all the work going into training a GAN and fine-tuning it, we're getting like these really marginal gains that may not be very practically or statistically significant, and then also use that to segue into our semi-supervised approach, which actually has the best test set performance over all values of k. From these experiments, we made some interesting observations. Which is that increasing N of S, the number of samples per class, beyond the point actually makes validation and test accuracy worse. And in practice, this can be as small as 10 for any k, whether that be 5, 10, or 15. So if it's 10, then that's roughly 100 examples, 100 GAN-generated examples in total, because we have 10 target classes, so 10 times 10 is 100. And you might wonder, why is this the case? Well, in addition to the difficulty of fine-tuning any sort of generative model on a small set of examples, the training dynamics of GANs also comes into play here. We know from the very extensive GAN literature that just with the training dynamics of GANs, they definitely favor sample quality at the expense of mode dropping. Compare this to something like VAEs, where the trade-off is in the opposite direction, where with VAEs, sample quality is generally not so good, but it basically does try to cover all the modes of the data distribution. We actually corroborated this conjecture basically with these precision and recall metrics that were recently proposed in the GAN literature. And they're interesting in that they measure two different things, and so precision can be thought of as basically measuring sample quality, and recall can be thought of as measuring mode coverage. And basically precision and recall both affect FID. And while FID is a convenient metric because it kind of summarizes both of these at the same time, it's also a bad thing in this case, because we don't really know what is affecting our performance more. And so in some cases, like this analysis, it's actually nice to measure these things separately. And so we'll show that in the next slide. Okay, in this slide we have a box plot, and basically what we're showing is for each k equals 5, 10, 15 on EMness, we're basically showing the distribution over the different dataset seeds of precision and recall. Where precision, as we said earlier, amounts to basically sample quality, and recall amounting to mode coverage. And if we just consider just just the regular non-semi-supervised variants, we can basically see that that recall definitely lags behind precision for all of these experiments. In fact, quite significantly. And so this seems to corroborate our conjecture that when it comes to using examples generated from the GAN, even though they appear to look pretty decent, they do not reflect a lot of variation or diversity. And so when you combine those with the examples in the support set, if you combine too many of these generated examples, then the classifier, when we fine-tune it, it ends up overfitting to these like very non-diverse samples, right? So there is like a discrepancy between, let's say, the true validation, the ground truth for the target classes and the generative distribution induced over those labels. And obviously, if there's a discrepancy between them, then this can basically make the classifier overfit to that distribution. And so that's really reflected here with the extremely small recalls that we're seeing. Another very interesting observation is this. This K-shot data augmentation stuff is and can be very difficult precisely because of what we call the K-shot dilemma. So for instance, when we have a small k, it makes it really hard to fine-tune a GAN to generate well from that target distribution. But that is when we need data augmentation the most, right? So if we just consider something like really small, like k equals 5, well, it's going to make it very hard to fine-tune a GAN. But because we have so few examples per class, that's when we really need that data augmentation. Conversely, on the opposite end, if we have a very large k, let's say k equals 10,000, well then it makes it very easy to fine-tune again. But then we might expect diminishing returns, right, when it comes to fine-tuning the classifier, because it might be very hard to improve over a baseline that uses 10,000 examples per class. And so we can think of it as sort of being on a spectrum where if this was k, things aren't so great when you're in the low k regime, and things aren't so great when you're in the large k regime, and then maybe there's a window in between where one can actually get benefits with this approach. But now this makes the practical application of everything we've discussed way more difficult. And I like to see this as really one of the main takeaways from this work. Is precisely this dilemma and why it's so difficult to achieve practical gains in this scenario. Now, to address this dilemma, one very easy thing we can do is basically just relax the problem formulation so that we can actually do semi-supervised learning. Right? Because in the real world, we may not have lots of labeled data, but we might also have lots of unlabeled data. And so, this is something that can definitely make this overall approach more pragmatic, is to basically leverage unlabeled data into the training. And so now this is when we're going to particularly focus on this discriminator here and how we can modify the training of this and also the training of the generator so that we can leverage unlabeled data in a very straightforward manner. In this slide, I'm showing the projection discriminator from Miyato et al. So I'll just write that down because I forgot the citation. So if we just look at this equation, this is basically the output logits of the discriminator before the sigmoid is applied. And basically, at first it seems a bit esoteric, but really it's a summation of two terms. Where one of the terms we're basically doing this, we're basically embedding y, right? So y is a one hot embedded label, and v is an embedding matrix, and we also have these linear layers. Well, the motivation for this is really, if you look at the paper, the original paper. Basically, this equation here is really trying to approximate the ratio of these joints, right? So you can think of one of these as basically being the learned generative distribution, and one of these as being the ground truth distribution. And through Bayes' rule, we can actually expand this out, which in turn means we can actually expand this into a summation of two log ratios. And it turns out that this term is actually really trying to approximate this, and this term is actually trying to approximate this. But the interesting thing to note is that this here is not dependent on the label. And if we were to look at this diagram, if we actually look at how X and Y flows, is that basically, after all of these complicated looking arrows, you basically get this output d of X and Y. But if you just compute this, which is not being conditional on a label, then basically you can define this output d of X, which would be the logits for the unconditional branch of this discriminator. So to be more concrete, what we can actually do is that during the GAN fine-tuning stage, we can actually define a new set of losses that will be optimized in addition to the regular supervised losses for D and G. And so here, we have d of X, which is the unconditional branch for the discriminator, and we can just write that uppercase d of X is just the sigmoid of this output. And essentially, we just want to measure whether X is real or fake without regard for the label. And so that's reflected here. So for D, D obviously wants to maximize the probability that for a real X from the validation set that is real, and then conversely, basically maximize the probability that that a generated example here is fake. The generator stays conditional, but we're just evaluating it on this unconditional branch here, where basically the Y's are being sampled from the validation set. And likewise for the generator, it actually wants to maximize the probability that a generated image is real. And you'll also note that this is weighted by a hyperparameter alpha, which is really important because if it's too small, then we're not really weighting the importance of using that data. But if it's too high, then we don't want to basically run into a degenerate situation where the conditional GAN just turns into an unconditional GAN, and we wouldn't want that either. So this is a hyperparameter that's very important that we'll also have to tune. So going back to the box plot that we showed earlier, showing the distribution over dataset seeds for precision and recall, we can basically see that with the semi-supervised formulation, we really are able to close the gap between precision and recall, which is great. And these will be reflected also in the table of results that we'll show again. Just to wrap things up a bit, we also show results here on Omniglot for K equals 5, and we show the results we got on the validation and test sets. Unfortunately, we didn't manage to get any gains here, with actually the test set numbers for the baseline being the highest. But it's also worth noting that Omniglot doesn't really fit well with our training assumptions. The issue with Omniglot is that there's really only 20 examples per class out of 1,600 classes approximately. Whereas we kind of assume that our training classes are actually abundantly represented, and so that for all the training classes there would be lots of examples per class, and that would kind of make for a good foundation for the GAN when we pre-train it, and that's not so true here. So despite the simplicity, it seems, of Omniglot, it was actually really hard to get working in our particular case. We also have results here on CFAR10 for K equals 50. In conclusion, though the best results we have were achieved with a semi-supervised formulation, it is still quite difficult to achieve practical gains. And so one example of this was, as we said a few slides earlier, this whole idea of there being a K-shot dilemma, where if K is too small, it can be very hard to fine-tune a GAN, but if K is too large, well then we can kind of expect diminishing returns when it comes to improving classification performance. Despite this, we've still demonstrated that one can achieve gains in FID and precision and recall by careful fine-tuning strategies, but also with our semi-supervised formulation. VAEs and GANs generally are quite awkward for few shot, just because of the whole sample quality and mode coverage trade-off. So like I said earlier, VAEs tend to prefer covering modes at the expense of sample quality, whereas GANs do quite the opposite. But there's been a lot of recent development in diffusion and score-based generative models. And these should actually be explored in future work instead of VAEs and GANs, because they actually do quite well in terms of both mode coverage and sample quality, even if that might be at the expense of sampling time. But ultimately, making deep neural networks more data efficient is still quite a fundamental research question. And we've seen that basically your fine-tuning on very small amounts of data is still a huge bottleneck, and that certainly affects the degree to which we can achieve good performance with this approach.